recording. There we go. Okay. So we're recording. I just found this article, it was in my feed the other day, and I just thought it's kind of interesting. Um, because that's exactly what I have been trying to teach, critical thinking. How do you think? How do you process information? And how do you learn? All of those things are a part of what I want to teach, not just computer architecture and programming and stuff like that. Okay. The technical stuff, you can probably learn by yourself, but I think the more important part is, learning how to think and how to learn itself. um, but anyway, I'm not going to go into the details of this particular article. You can just look up, psychology today and a few words from here, which is, why I stopped caring about, enhancing everyone's, thinking. Just, look for certain keywords and you'll find it. So it's kind of interesting, because, it is not something that can be taught unless the recipient is ready. Okay. So that's one of those things where, you can try all you want. Okay. But sometimes, when people are not quite ready to accept what they think or what they know is, should be questioned, then, that person is not ready to learn critical thinking yet. So anyway, it's just kind of interesting. I want to share with you guys. All right. So getting back to the topic that we are already on. Okay. So last time we talked about, what a um, SR latch is. And the way I describe an SR latch in terms of a circuit is through text. Okay. So I could have easily, okay, even easier than typing, I could have easily made the circuit and just say, okay, here is our SR latch. I could have done that. So now the question is, why do I use text to describe a circuit? In other words, I use, C++-ish, language. This is an AND2, N1 is an object of that type, N2 is an object of that type. This is a class input pin. S is an object of that class, and so is R, and so on. And then the connectivity between the components are using, circuit is an object. It has a method called add node. And in order to specify a new node, you use new, and then you create an object called a node. And this is the list of things, that belong to the same node. In other words, I'm using pseudocode to describe, how a circuit is supposed to be. So why do you think I kind of switch from logisim into this particular method to describe a circuit? What am I trying to get you guys to, think about? hmm And it is, so imagine you're trying to design a complicated processor, okay, like a CUDA processor of the NVIDIA, chipset, okay. How complicated do you think that diagram is going to get if you use the logisim approach? It's going to be quite complex, right? The problem with graphical representation is every time you want to edit something, you kind of have to move things out of the way, put the new thing in, and then reconnect a whole bunch of things, and so on and so forth. It's not easy. It's because of that reason that we do not program in flowcharts. Okay, we do not program in graphical programming languages. We program in text programming languages because text programming languages just makes it so much easier to automate things. You can have macros. You can, also, edit. You can also have structures and so on and so forth a lot easier when the specification is in text as opposed, to it is graphical. Yes. Mm-hmm. Yep. Okay, but how complex? Right. Exactly. Yep, exactly. So do you want to be the computer engineer who doesn't quite know how to design a computer? Exactly my point. So all the professional jobs to design chips or design computer components, they all use one of two languages. One is called Verilog, 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 and the other one is called a VHDL, and they are both HDLs, hardware description languages. Okay, and HDLs is basically text description that allows you to specify, the connectivity between the circuits, and then you can have quote unquote functions, you can have abstraction, and so on. Okay, um, we are not going to deal with VHDL or Verilog in this class because we have Logisim. So Logisim is great for this class because the kind of processor that we do is not so complicated that it cannot be done using Logisim, but even with the tiny little processor that we have for this class, it is getting complicated. Okay, it fills up the entire screen with all kinds of symbols. Okay, so it does get it's easy to get lost, in that particular design. So that's the reason why I switched to a text description just so that you have some exposure of oh, okay, we can use text to describe a circuit. Yes, we can. All right. So now we're moving on to the last portion. Okay. Did anyone give test out the um what I suggested you guys to try out, which is you start off with the two input pins of the SR latch to be zeros, and then you switch both of them to be ones at the same time. Did anyone give that a try? Not yet. Okay. So give it a try. Okay. Um the module actually describes what happens when when something like that happens. So it basically leads to oscillation. In other words, it will never reach a steady state. Okay, the two NAND gates will keep alternating their outputs to ones and zeros, back to ones, back to zeros, and so on. The circuit will never settle on a steady state. But it is a good exercise, okay, because in that exercise you will understand why. I mean, otherwise, people look at this circuit and go like, "Oh, we can just try out everything in Logisim and we can understand the behavior of the circuit." Yes, okay, with simple circuits we can do that. But you know, Logisim cannot figure out that there's the circuit has entered a state that is oscillating, where that's not going to be a steady state anymore. Okay, so it's only through the analysis that we have done, which is separating the two phases. We have NC, node connectivity, and we also have PD, which is propagational delay. So only through that analysis we can find out that, oh, okay, this circuit will never settle on a steady state ever again. Yes. Yeah, it does. Yeah, but it doesn't understand. So the way it understands, it has entered an oscillation is because that's the mechanism that it uses internally in order to find out, okay, what is the next step? What is the next step? And then it finds out that without changing the input pin, it got back to the same state that it was in a little bit earlier. So that's how it can detect that it has entered, the uh, oscillation. But you're correct. Autism can detect it, but it doesn't explain it. It doesn't really. And when you observe your logism detecting that it is in an oscillation, you don't understand either because the mechanism of why the circuit entered into an oscillation state instead of a steady state can only be explained when you go through this process and go like, oh, okay, through these propagational changes, we went back to an earlier state, which means it's going to repeat this whole cycle over and over again. Does that kind of make sense? All right. All right. So with the SR latch out of the way, we are going to look into something bigger that makes use of the SR latch. So this is called a D flip-flop or level sensitive D flip-flop. And the circuit is described exactly like this. It is in text. So what we'll do is we are going to convert this into a Logisim circuit. Then we can play with it a little bit. Okay. So that's what we're going to do now. And let me start up Logisim and then we will go ahead and play with it. So it's way too big. I just have to kind of shrink it all the way down to the size that we need. Okay, there we go. Okay, that's a little too small. I'll adjust. There we go. Okay. So the first thing you notice about the components of a level sensitive D flip-flop is, oh, I need an SR latch. Okay, the SR latch is a component of a level sensitive D flip-flop. So what I need to do now, okay, in LogicSim is to make a function or a subroutine by saying go to project, add circuit, and we need an SR latch, like so. Okay. So once we get here, we just create an SR latch. Okay, we have two input pins, two output pins, and then two NAND gates in between that are kind of cross-wired, okay, cross-connected. Wouldn't say cross-wired, but cross-connected. So here's a NAND gate. We only need two inputs from each of the NAND gates, and I don't need it to be gigantic like so. So this is the one of the NAND gates, and I can even make things look nice by aligning things a little bit here. So here's the other NAND gate down here, and this is the output of the other NAND gate. And we hook up the wires like so. And then now we have the crossing. Okay, so this wire crosses over to the input of the other NAND gate, and then this wire crosses over to the input of the other NAND gate like so. And now we have a SR latch. Okay, so now we go like, okay, good. And then what we'll do is we are going to label the whole thing. Okay, so we'll specify. So technically what we call the X pin is S for set, and then what we call the Y pin is R, which is reset. And then we have Q, which is the actual output, and then we have NQ, which is the quote unquote negation of the output. It's not always the case, but close enough. So now we just have to put these things into the correct location. It's good to use captions, so this way, when I use the SR latch as a component, I know which pin is which pin. So put Q all the way over here, and we'll put NQ all the way over here. And obviously, this is not going to be my main circuit, so we're going to have to change the name of the circuit here so that it is not the main circuit anymore. So go back to the main circuit. Oh, okay, this is the SR latch. Never mind. Okay, I created the SR latch to begin with. All right, so now we go to edit circuit and then go to edit circuit appearance. Everything is good. So now we'll go ahead and make the level sensitive D flip-flop. So I'm going to go to project again, add another circuit. This time I'll call this level sensitive D flip-flop. And then we will collect all the parts that we need. We need two input pins, D and EN. Okay, so we have D, which is data, and then we have EN, which is enable. And then we have two output pins. One technically only one is really needed. We just we just need Q because NQ is the opposite of that. But since the circuit calls for that, we'll also have Q and NQ, and then we'll label the pins correctly. Okay, so this one is D for data. This one is EN for enable. This one is Q. I don't understand why Q is used as the symbol for the output, but that's what it is. Okay, and some of you can probably look it up and find out why exactly the letter Q is used for the name of the output of a flip-flop. Okay, so now we also want to collect the other parts. Okay, we have two NAND 2 gates. Okay, N1 and N2. So we go to gates again, and then we go to NAND, and then we specify this, change the number of inputs back to 2, change the size, duplicate, name each one. One is called N1 and one is called N2. Okay, so N1, and then we have N2. We also have a NOT gate. Okay, the NOT gate is just negation. So here's a NOT gate, and it has a name also. It is just NOT gate N. And now we have almost all the components because we just need the SR latch itself as the last component. So we go to SR latch, make a copy of that, and it has a name of SR. Okay, so we'll go to label here and call it SR. So now we have all the components. So once we have all the components, it is time to take a look at the nodes. Okay, in other words, which port of which component connects to which port of some other components potentially. All right, so we just now whether you take notes right now or not is up to you, but I can tell you that your lab today is similar to what I'm doing right now, although not exactly the same. So whether you take notes or not, depends on whether you are familiar enough with Logisim already and kind of know how to do things in Logisim already. All right, so the first node connects D as a pin to the in0, the first input pin of N1. Okay, so I'm going to have to move things around a little bit just so that it is easier to do that. Okay, there we go. And also the N, the input of N, which is the NOT gate here. Okay, so I'm going to put this one maybe up here. There we go. So I'm just positioning things so that they are easier to make connections to, like so. There we go. So I'm now done with the first node. The second node is about the EN. It wants to connect to the second input pin of N1 and the first input pin of N2. Okay, well that's pretty easy. Okay, so we just hook it up like this and then like that. Okay. The third node connects the output of the NOT gate to the second input of the N2, which is a NAND gate. So we take this, oh, no, no, the NOT gate, right? This one here, this one here. Well, I suppose I can just route it around like so and hook it up here. There we go. So now we're moving on to the fourth one, which is looking at the output of N1 and hook it up to the S pin of the SR latch. So that would be good. And then we look at the third to the last one, which is the taking the output of N2 and hook it up to the R input pin of the SR latch. And the rest is super duper easy. The Q of the SR latch connects to the output pin of the same name, and then the NQ goes to the output pin of exactly the same name, like so. Okay, so now we are done with creating the level sensitive D flip-flop. Now, just by the name of a level sensitive D flip-flop means there are probably other kinds of D flip-flop. The lab that you're going to do is the other kind. Okay, all right. So now the question is, well, how does it work? Well, a level sensitive D flip-flop is pretty easy. Okay, the enable pin is here to basically say, is the circuit going to copy whatever the D pin has to the Q pin? The NQ is always the opposite of the Q pin. Okay, that's all it does. It just copies whatever the D pin has to the Q pin of the entire circuit. But it will only do that when EN is a 1. In other words, when it is enabled. So right now EN is a 0, which is disabled. So that means at this point, I can use the poking tool and I can change the D pin all I want, and nothing happens to the output pins, right? But the moment I enable the circuit, it copies. So right now it is enabled, which means whatever I click, whatever the state of the D input pin is now mirrored directly to the Q pin, and then the NQ pin is always opposite to the Q pin itself. So if you compare this circuit to just an SR latch, this is more usable, okay? Because now we have control over whether the D flip-flop is remembering the input or not. In other words, when enable is a 1, we are telling the circuit, okay, remember what the D pin has as the output Q. When the enable is off, then it's not going to do a single thing. You can change the data input pin any way you want, and it's not going to change the output Q pin. Yes? You cannot. So in this particular circuit, there is no way to make them both um, ones or both zeros. All right. So your exam may involve tracking down the NC and the PD of something like this. Exam 2, yes, not the one on Thursday, but exam 2, which means it does not hurt to kind of go through the analysis to find out, oh, if I change one of the input pins from a 0 to a 1, what's going to happen to the circuit? And then if I change the other one also from a 1 to a 0, what is going to happen? Okay, so those would be really useful exercises from your perspective in order to understand how this circuit works. Yes, use case of, well, this is the simplest kind of D flip-flop, so to speak. In other words, it can remember one bit. Okay, you can say, "Hey, D flip-flop, I have something for you to remember. It's either a one or a zero," and then you can say, "Okay, now go ahead and remember it." Okay, the data is now available on the data input pin. Now you can remember. But then after that, you can turn off the enable, and then whatever is connected to the data pin can now change to whatever it wants to, and it's not going to affect the output of the D flip flop because it has quote unquote memorized the input when the enable was on earlier. So that is correct. So if you turn off enable, then you can do whatever you want with the data input pin, and you can see how the output stays the same. Well, oh, okay, but do we know why there's an error? Okay, so let exactly. So if I were to go to simulate and reset the circuit, you can see that the SR has an error. So why is that? It's because when we reset the circuit in Logisim, all the input pins by default will turn into zeros. That's just a part of how the reset works. But when both input pins are zeros, this input pin goes to N1, and N1 only needs one of the input to be a zero for the output to be a one. Okay, same thing for N2. Okay, it only needs one of the input to be a zero for the output to be a one. So what is the behavior of an SR latch when both inputs are ones? It's no change. Okay, it maintains the quote unquote current state, but we never gave it a current state to begin with, and that's why the output of the SR latch are quote unquote errors because it cannot determine what it should be. Okay, yes, it is, yeah, it is a kind of garbage value because if you right click and go to the SR latch itself, that's exactly what is going on. Because if all we know is one of the input pin of the NAND gate is a one, we don't know what the output is supposed to be. And the same thing applies to the bottom NAND gate. And as a result, in this case, because the output of the first NAND gate, which is unknown, is fed to one of the inputs of the second NAND gate. So the second NAND gate is unknown also, and it forms a critical loop. And we can never resolve what the output of the NAND gates should be, even though we know what both inputs are look like because we know one of the input pin is a one, the other input pin is also a one, but that is not enough for us to resolve what the NAND gates should be outputting. And if we cannot determine the output of one of the NAND gates, then we also cannot determine the output of the other NAND gate. It becomes circular in that sense. Does that make sense? So that's why, when we created the circuit, the output of the SR latch is quote unquote E or error, which basically means in this case, the circuit, the simulator cannot determine what it really should be. Okay, so that was a very good question. Okay, that's critical thinking. Okay, you look at something, you go like, why is it like that? Okay, I kind of need to know why it is like that. All right, so are we doing okay? All right. So as I said a little bit earlier, it is useful to understand how to go through the NCPD analysis of a circuit like this, okay, if you just kind of go back to earlier, how I exercise the various pins, you can kind of use those as an example. I'll do it one more time, just so that you guys, if you want to, you can go through that exercise. So I use the poking tool. I change one of them to a one, and keep flipping and flopping. Nothing happens to the output pin. But the moment I change the EN, now everything settles. But as long as the EN is a 1, I can change the D pin and the circuit keep changing the output pin. In other words, the output state and the input state remain exactly the same as long as EN is a 1. But if I turn EN to be a 0, then the input pin no longer changes the output pin. And this is called a level sensitive D flip-flop. Yep, to be what? To be EE, um, resetting the circuit. So if you do a control R to reset the circuit, that is when it becomes E. Because when we reset the circuit, the input pins by default turn into zeros. So because both input pins are zeros, the output of the outputs of N1 and N2 are also going to be ones. And as a result of that, the SR latch sees its input as both ones without exposing to one of the other configurations before. And as a result, the SR latch does not know what am I supposed to remember. You're telling me to keep the state of the output, but what was it? We never specified. Is that okay? All right, cool. So this is a level sensitive D flip flop, and your lab today is to work with what we call an edge sensitive D flip flop. So with the edge sensitive D flip flop, it works a little bit differently. Okay, so the way it works is you have an edge. Okay, you have a pin that is called a clock pin. So you present the input. Um, still a data pin, but there's a clock pin this time. The device remembers the input only when the clock pin goes through a rising edge transition. So when the clock pin goes from 0 to 1, at that moment, the circuit remembers what the input is, and the output is the same as the input. But after that transition, you can change the input pin all you want. It does not change the output. Okay, so it's called edge sensitive. So we are not going to take a look at the circuit because that's kind of your homework assignment, or not homework, your lab. So your lab involves reading this part here and turn it into an actual circuit. Okay? It's okay. It looks a lot worse than it really is. Okay, you just have to go through the steps one by one in order to make the correct connections, kind of like what I did a little bit earlier. And that's why I said, well, you might want to take notes when I was doing it because you might need to do something very similar. Not exactly the same, but very similar. All right, so that's an edge sensitive. And now we go through, some of the analysis here. And then we go through something that is now both clocked and gated. Clocked means it is edge sensitive. Gated means it's level sensitive. So this is kind of like a combination of the two. So with this circuit, we have a clock, which means it is quote unquote edge sensitive or clocked. Okay, so when we use the term edge sensitive, it is the same as clocked. It is also gated, which is also the same as level sensitive. So we have clock, we have enable, and then we have data. So the way this particular circuit works is if enable is off, nothing happens. Okay? When enable is a 1, then it will still take the clock to go through a 0 to 1 transition in order for the data input pin to be reflected to the output Q pin. So one way to look at this, okay, I know this analogy is not going to be very helpful anymore in the near future. If you think about this as a camera, okay, the enable is kind of like the on-off, of a camera. If the camera is off, you can click the shutter release all you want, nothing happens, right? So the enable is kind of like the on off of a camera. The clock is more like the shutter release button, okay? And if for those of you old enough to know what a camera is, the shutter release is something that you press once and then it captures one single frame, and capture the image. So that's kind of what the clock is. The data input pin is kind of like the lens, okay? It is where the image is coming in, and the Q pin is kind of like the film, on the back of the camera, which stores a copy of the image that is coming through the lens. So you can kind of think of it in that particular way. Are we doing okay so far with this? So based on the description that I told you, you can also give yourself, an exercise of going through the whole thing like, okay, let's assume all the pins are unknown to begin with, and you're changing all of these to zeros, initially. And then you go like, okay, these are all zeros initially, and then the first one you change from a 0 to 1 is the EN, and then you're gonna change your clock from a 0 to a 1, which creates the edge. Then you follow all the changes throughout all the components and see how the Q pin becomes the same as the data pin, which is also a 0 at that moment. Okay, so that's an exercise that you can always do so that you can, one, you practice the PDNC whole thing, analysis, and two is to get a better understanding of a clocked and gated D flip flop. Is that okay? All right. Yep. Go ahead. The data pin is presenting what information the device is supposed to remember. So if you present a 1 at the data pin, the enable is a 1, and the clock goes from a 0 to a 1, then the Q pin will become a 1. Basically, the Q pin will mirror whatever the data pin is when EN is a 1, and only when the clock is going from a 0 to a 1. Okay? All right. So you would think, this should be it, right? No, not yet. Yep, go ahead. Hmm? Yeah, S and C. No, the C is its own SR latch. There are two SR latches in this particular design. I just call one S, the other one C. There's two SR latches. That is correct. Yep. But this is also why it is important to understand the SR latch first, because without understanding the SR latch, this circuit is going to be kind of difficult to draw and understand. All right. Are we ready for the next one? So you would be asking, what else can we add to the whole thing? Okay, we have clocked, which is edge sensitive. Then we have gated, which is level sensitive. So what else can we add to the design? Well, we can make it resettable. Okay, so the last detail here is we have one additional input pin called reset. So this is the reset pin. The reason why it is important to have a reset pin is because when you start up a computer, there's no known state. Okay, so that means the SR latches, especially the SR latch, the last one, is going to have some state, but the state that it is in is really just kind of random. Okay, so do you want, the components of your computer to start up completely in a random way? Probably not, right? So you want it to start at a particular state. Well, fortunately, there is a chip of your entire computer and your cell phone and also your fitness watch and stuff like that. It is called a watchdog. Okay, it's called a watchdog chip. So the way the watchdog chip works is kind of funny. It is supposed to be hit like periodically. So every watchdog chip has a certain specification. Some needs to be hit like every 2 seconds or less. Other ones may need to be hit every 5 seconds or less. Anyway, so it's basically a dead man switch. So if you don't hit the watchdog within the specified period of time, the watchdog is going to reset the whole thing. It will activate a reset signal, which is kind of the reset signal or the reset pin here. So when you first power up the computer, when the power supply to everything is unstable, okay? Because if you think about the chips, okay, let's say we are talking about really old TTL chips, okay? So the power supply is supposed to get to 5 volts, which is the nominal voltage for those chips to function. Well, do you think when you power up a computer, the voltage of the power goes from 0 to 5 like instantaneously? Does that happen? Nope. It's going to ramp up to from 0 to 5 volts. Now, from our perspective, it looks like it's instantaneous because our scale of time is different from the scale of time of a computer. But from the scale of the computer, it is taking a long time to ramp up to 5 volts. So before it gets to the healthy 5 volts, you probably don't want your computer to start to do stuff, okay, because things are not stable yet. So the watchdog chip is also responsible to take a look at the voltage, the supply voltage to the chips. And if it is below a certain point, it will hold the reset, like the reset pin that we see here. It will hold the reset, it will assert the reset for a certain period of time until the voltage is stabilized. Then it will release the reset, and then things can start to happen at that point. Is that okay? So that's the concept behind how computers start up when you first like power up the computer. So if you think about this particular reset, now this one is called active low, which means we are resetting when the reset pin is a 0, not when it is a 1. So think about what happens when the reset pin is a 0 in this case. Where is it going? The reset pin is going to this AND gate here. Um, and if a 0, if one of the input of A3 is a 0, what is the output of the AND gate? It's going to be a 0, right? So it's going to go to the reset pin of the SR latch here, and this will become a 0. What about OR 1? Okay, this is O1. The reset pin is a 0, and this is a negation. When you see a bubble, it is a negation. So the 0 becomes a 1. If at least one input of an OR gate is a 1, what is the output of the OR gate? It's going to be a 1. So that means S is going to be a 1, R is going to be a 0. Does anyone remember in that particular input configuration, what would be the output of the SR latch that we call SRC in this case? It's going to be a 0. Okay. If S is a 1, R is a 0, the output is a 0. But the important part is it is no longer unknown. Okay. So the reset pin does just that. But the reset pin bypasses everything else. Okay, it ignores the data pin, it ignores the enable pin, it ignores the clock pin. It just goes straight to the very last SR latch here and go like, you will remember a 0. That's all it does. Okay, so inside your computer, you have a lot of components. Okay, the processor, the GPU, blah blah blah. They all connect to the same global reset for the entire computer. So when your computer starts up, it resets everything to zeros. What about the blue screen of death? How does that happen? It has to do with a watchdog. So what happens when Windows just kind of craps out, when it goes like, oh, okay, I'm totally lost. One of the device driver is faulty because usually it's a device driver that causes the blue screen of death because only that has sufficient privileges to do things bad enough to cause a blue screen of death. Yes, exactly. So somehow the blue screen of death has to do with the watchdog. So that's because when Windows and Linux and Mac OS and all kinds of modern operating systems, when they're healthy, there's a timer that goes off like every so often, like every 10 millisecond, 20 millisecond. I don't know exactly the period of time, but anyway, so they periodically hit the watchdog. It's like, okay, don't reset, I'm still alive. Don't reset, I'm still alive. Don't reset, I'm still alive. Okay? And then here comes the faulty Windows device driver, crashing the whole system. Okay? So the timer cannot continue with this mechanism anymore. So the watchdog goes like, okay, I'm waiting for you to tell me that you're still alive, but I have not received that message for 5 seconds. I think something has gone really, really wrong. What am I going to do? I'm going to hit the panic button. The panic button is called the NMI. NMI stands for non-maskable interrupt. In other words, no matter what your CPU is doing, probably something it's not supposed to, NMI is going to say, stop that and do this instead. What do you think that something do this instead? What do you think that is? It goes through the code to give you the blue screen of death. There's no intervention until the blue screen of death gives you an option. It's like, do you want to save? Do you want to dump the memory content onto your hard drive? That is what the blue screen of death is. Every operating system has a equivalence of the blue screen of death because when the watchdog doesn't get hit every so often, then something bad is assumed to have happened, and then the NMI kind of kicks in and go like, okay, we're gonna do this. Okay, we'll just do a core dump. Does anyone know what a core dump is? Okay, go ahead. Into a dump file, into a binary file. Basically, all the content of the entire memory space is dumped onto a single file, and then the computer just goes like, "Okay, I'm gonna go to sleep now." Yep, processes. Yep. What was running at the time? Huh? Sorry, XSD, XXD. So is that the extension of the file? Oh, to read. Okay. Yeah, yeah. Binary core dump is one of the most important part if you want to do forensics. If you want to know what caused the blue screen of death, the core dump is the first thing you need to read. Okay. So yes, I know I kind of digress a lot, but it is important to understand what is the reset pin here, what it does, and what is going to hold the reset pin, what is going to assert the reset pin under what situation. Yes. Well, I think we can attribute that to closed source versus open source. So because most of the blue screens of death is caused by poorly written device drivers. Now it's not like there are no poorly written device drivers in Linux. There's plenty, but because it's open sourced, when something crashes, somebody's gonna go like, okay, I'm gonna have to go fix this, okay? Because there's always somebody who wants to fix things, right? So then when they see, okay, something has blown up, it's not working, they would go in and they're gonna fix it. But in closed source, in the closed source ecosystem, so to speak, nobody can get into the source code. Even though I want to help, this proprietary chip manufacturer to debug the device driver, I don't have the source code. So I think that's why, bugs like that is less likely to be fixed earlier in a closed source environment as opposed to an open source environment. Um, So that can also translate to Apple may have better software engineers. But there are definitely devices that are not from Apple, like the NIC, network interface card, is not from Apple itself. The Bluetooth chipset is probably not Apple's own thing, but the supplier of those things, will have to supply the code, and then Apple would probably have to go through some, internal testing just to make sure the drivers are good to go. One of the companies that is actually well known to put out faulty, device drivers is Qualcomm. If you read up on Qualcomm Linux, device drivers, you'll find all kinds of, kind of like, oh, who writes program like that? You know, I'm not sure. Oh, that has multiple things going on, not just, closed versus open source, man. That's a whole different thing. All right. So does everybody understand how the reset pin is capable of resetting the final stage, the last stage SR latch, so that it starts with a known state of zero whenever the reset pin goes to zero, in this case? Yes. Mm-hmm. Yep. Yep. It bypasses everything. The reason why it bypasses everything is because when the reset is a zero here, A3 will output a zero regardless. And then O1 will output a 1 regardless of what the earlier stages of the circuit is doing. It doesn't care. It simply does not care. And the reset pin is usually not held down for a very short amount of time. Usually it would be in hundreds of milliseconds to make sure that, you know, it clears, whatever is the cause of the problem. Yep. All right. Do we have any questions about this portion of the discussion? Okay. Probably not of much interest other than to people who want to design chips or people who want to put components together on the circuit board so that they can make their own custom computers. So it's kind of interesting. I mean, this is the kind of work that I did before I started teaching. And for those of you who may not know this, okay, there's a architecture called the ESP32. um, it is an interesting platform. I mean, you can buy ESP32 based, computers for dirt cheap, like that. Okay, but it is a fairly capable processor. It can interface to like screens. It can interface to compass chips. It can interface to accelerometer and a whole bunch of other stuff. Okay, you can get a small thing, okay, about yay big, that has the processor, a small display, even a battery, even a lithium ion rechargeable battery for like 20 something or 30 bucks at the most. Then you can start to implement your own thing, okay, on that chip, on that device, to do whatever you want it to do. And it comes with, oh, by the way, it comes with Wi-Fi and all that good stuff. Wi-Fi, Bluetooth, it's already there. It has a USB-C connector too. Yep. Well, it has. That's how it gets its power. Oh, that's easy. Yeah, with this thing, yeah. All you need to know is to emulate, as a USB device, and that's one of the things, where people can easily do, even for things that are not a USB thumb drive, like a camera. So if somebody was to be malicious, they can put in the firmware in a camera or something that is not even a thumb drive, so that when you plug it into a computer, it mounts as a storage device and will mount as a CD-ROM or a DVD device, a read-only device. And depending on how you configure Windows, you can configure to autoplay when a CD-ROM is present, and then it will just run the installation software to install things that you probably don't want to be installed on your computer, just by plugging in a device that is not even a mass store device, like a camera. Yep. Yes. Yeah. They have, communication methods to talk to each other. I think some of these may be Bluetooth enabled, so you can even go through. You can use wireless communication talk to have these to talk to each other. Yep. Yep. So this whole thing, is called embedded system development. Basically you are programming computers that are not like regular computers or even, you know, computers pretending to be a phone. You're programming things that are really small, can be battery operated, hours at a time at least, and then you can just program it to do kind of whatever you want to do. A lot of applications, a lot of applications. All right, so getting back to where we were, over here. So the last picture, yes. hmm it does not go anywhere. It's simply not brought out to any of the output pins. So if you look at this particular circuit, which is the edge sensitive D flip flop, and you look at C as a SR latch, C dot Q is brought out to the output pin Q, but NQ is not going anywhere. We're simply not interested in the output. No, it won't cause any errors. You can always leave an output pin not connected to anything because it is not useful to you, but you never leave an input pin not connected. Because if you leave an input pin not connected, the input is still used by whatever device to determine the output. So having an input pin not connected to anything means it is quote unquote floating. In electrical term, it's called floating. When something is floating, it means whatever conductor is connected to the pin acts as an antenna. So if you walk close by, it might cause the antenna to pick up a one or a zero. If somebody is to microwave something next to the device, it might pick it up as a one or a zero. So in other words, it's just an antenna. Okay, the slightest change in the electromagnetic environment will pick it up and go like, oh, I think I'm seeing a one. It will start to hallucinate basically. So you don't leave any input pins not connected, but you can leave output pins not connected when they are not useful. You mean for output or input? Nope. For the output, you can simply leave it unconnected. Yeah, it's safe. Yep. Nope. Because there's no current. You have a voltage being present at the pin, but because it's not going anywhere, there's no current. So it doesn't draw any more power than usual. Okay. It doesn't cause any interference. It does not cause any, you know, EMF, EMI, electromagnetic interference. So it's okay. It's not a problem. All right. So now we're getting to the last one. Okay, the last one is it looks like this. Okay, let me scroll all the way here and take a step back. It looks like this. Okay, so each one of the rectangle here is guess what it is? It is a clocked, gated, and resettable T flip-flop. So I'm building up this circuit step by step in this module. We started off with an SR latch, which is a memory device, but it doesn't even work like a real memory device. And then we moved into a level sensitive or gated D flip flop, which allows you to say, yes, I want you to remember the input. No, 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 I don't want you to remember the input anymore. Okay, you can control it. Okay, and then we started to talk about the edge sensitive or clocked D flip flop, where you control the timing of the update. Okay, it's only at the instant when the clock transitions from a zero to a one that the D flip flop will mirror the input to the output. After that, you can change the input, the D pin all you want. Doesn't have any impact to the output. So, and then we added the circuit to make everything resettable, right? So that you can start with a known state when the computer first starts up. So this one is basically having a whole bunch of those things. Okay, each one of these is a gated, clocked, resettable D flip flop. So what are we doing with this circuit? Let's take a look at the uh, connectivity of this particular thing. So the first thing we look at, okay, we'll just use a directional thing. So we'll start with the clock pin here. So you can see how the clock pin is multi-dropped. In other words, the same clock pin is dropped here, 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 and so on. Every single D flip-flop here shares exactly the same clock. What does that mean? That means they all update at the same time. Okay, so the clock pin controls the timing of the update. When do we update? What about the D pin? Okay, so the D pin is the only thing that is changed from before. Before the D pin is a 1-bit pin, now it is an 8-bit pin. It is an 8-bit pin, but using a splitter, I split it into these 8 individual bits. Bit 0 goes to here, bit 1 goes to here, bit 2 goes to here, and so on. In other words, what I have done is I'm just extracting each and every single bit of the D input pin and say, oh, bit 0, you go to one specific D flip-flop. Bit 1, you go to the next D flip-flop, and so on, which means every D flip-flop is responsible to remember 1 bit of the A-bit input in this case. The input is 1 byte, but each D flip-flop is only responsible for one of the bits of the byte. Is that okay? All right. What about the next one, the enable? Okay, so when you look at the enable pin, it is also multi-dropped, which also means when the device is enabled, in other words, it is allowed to remember something, all of them are allowed at the same time. Okay, so that part is synchronous. And then the reset is the same thing. If I reset, all 8 of them will reset at the same time. What about the output? Okay, the output of each D flip-flop, which is the Q pin, they come out here and they all go to a merger, which is basically just a reverse of a splitter. So the merger will take the output of each of these D flip-flops, merge everything back into an 8-bit output pin of Q. In other words, this is just a fancy way to say, oh, instead of remembering 1 bit at a time, we are now remembering 8 bits at a time. That's a register. So the term register is really just a multi-bit D flip-flop. A single D flip-flop can only remember 1 bit at a time. A register can remember multiple bits at a time. But the way they are controlled or the way they work is very much the same. Are we doing okay so far with the concept of a register? Okay. When was the last time that we saw a register in this class? The test driver. Yes, go ahead. Okay. Yep. So now I'm going to create a circuit. Okay. So we'll go ahead and create what we call a clocked circuit that can, that this is one of the simplest clock circuit that can be done. And it has its own. Okay. So what we're going to do here is instead of making our own register, which we can, but I'm not going to do it, we go to and pick up an actual register the, from Logisim itself. So I pick up a register. So I just dash the register here as a single device. So the first thing you look at a register is what is configurable with a register. So you look here, and it has 8 data bits in this case, which means it is configurable. If you want a wider register to store 16-bit at a time, you can change it. Okay. It has a trigger, which is the clock. So the trigger is on the rising edge, which means the register updates when the clock goes from 0 to 1. Okay. And it has a label if you want to. Okay. That's, so not a whole lot beyond 8 data bits and the edge of the trigger. But it has a lot of pins around it. Okay. So we'll take a look at the pins that are around, or the ports that are around it. This is a D port. Do we need to explain what the D port is? Okay, so that's the input, right? This is the information you want the register to remember is coming through the D port. The next pin down is, okay, we'll just hover the mouse pointer over it. It is the enable pin. Okay, so what does it do? Yep. But even when it is enabled, what else do we need in order for the register to update? Yep, and this is the clock. And this is the reset. Okay, so in this case, the reset is it resets when it's a one as opposed to resetting when it's a zero. Okay, so the polarity of the reset is opposite to what we described a little bit earlier, but nonetheless, it serves the same purpose. Okay, and then finally, we have the Q port, which is the output of the register. So basically, this is essentially a multi-bit gated, clocked, and resettable D flip-flop. That's basically what it is. So what we'll do is we are going to hook this up with an adder. So we go to arithmetic, get a little adder here, okay, because we're going to make a counter. So we look at the output, we use it to hook up to the input, one of the inputs of the adder. Carry in, which is this pin here, is essentially K0, the way we described the adder. So that's why K0 is not always a zero, because in terms as a circuit, D0, K0, sorry, K0 is corresponding to one of the input pins of an adder. And as a result, it is not always zero, even though most of the time we want it to be zero in this class. But when we apply the concept of an adder, it is not always. Yep. Kind of. Okay. So when we talk about memory, we'll cover that too. So a memory is kind of like a register, except inside the device there are multiple locations. So instead of just saying, "Oh, I want you to update now," now you also have to say, "Oh, which location do you want me to update?" So when we get to memory, we'll get to that particular discussion. But every time you change a register, excuse me, every time you change a variable, you are essentially changing a bunch of D flip-flops. Okay, just conceptually, they're all D flip-flops. But once you change it, you cannot go back and retrieve what it was before. Yep. hmm hmm Well, we're already done with the ALU, but what we are doing right now is a very simple circuit that can count. Okay, you give it the click, okay, you give it the clock, cycle, it will increment the counter by one. That's all it does. Okay, but it forms one of the most important parts inside the processor or any type of your digital circuit. So this one I just want to give it a zero. Okay, so I go back to wiring and use a constant of 8-bit, and I want it to be a zero. So I want 8-bit as a zero. And you can see that this is using hexadecimal. 0x is a prefix of a hexadecimal number, and this is just zero, and we'll put zero over here. So we are basically adding the output of the register with zero, but I'm going to specify a one as K0 as the carry input, because the output of an adder is technically whatever the two inputs are, the sum of those two, plus whatever K0 is. So K0 is the third component that you're adding when we specify an adder. So now, how do we know the output is correct? All I need to do is to go here, okay, well, maybe using a poking tool, just poke here. Okay, I need a wire to do this. Okay, okay, we'll just do a wire and then turn it back into a poking tool, and we can see it is a 1 already. In other words, right now, the circuit is taking the output of the register, which is 0, taking the second input to the adder, which is also 0, taking the carry in, which is K0 in the discussion that we have about the adder, add all three together, and this is the output, which is a 1. Okay, not really surprising. So now we hook it up, okay, we connect the wire all the way back to the input of the register. In other words, we just go all the way around here to the D port, and nothing happens because you would think, or someone would have think that, oh, this is going to go crazy. The circuit would just keep going from 00 to 01 and then go all the way to FF and then back to 00 again. Nope, nothing is happening. Well, for two reasons. One, it's not enabled. Two, it's not clocked. Okay, so there's no reason for the register to update at all. Okay, so that's why we need to hook up some additional circuits here. I'll use one input pin for the enable so I can disable if I want to. And then for um, the reset pin can remain unconnected, but I'm going to use an input pin just to make sure that we are not resetting the register. And then the last one, which is the clock pin here, I'm going to use a very special, it looks like an input pin, but it's not exactly an input pin. It's called a clock pin. So this is the clock pin. So what is special about the clock pin is even though if you want to single step, you can actually click it using the poking tool, the same way as any other input pin, it can also be automatically clocked. When I said automatically clocked, I mean if you go to simulate, you can go to text enabled, and when that is enabled, it will automatically turn the clock pin from a 1 to a 0, back to a 1, and back to a 0, and so on, at the frequency that you specify. Okay, but I'm not going to do that just yet. Okay, so what I'll do is I'm just going to use the poking tool to manually do this. Okay, so right now, if I do this, hey, nothing is happening. Tac, what's going on here? Why is nothing happening? It's not enabled. Enable has to be a one in order for the circuit to respond to the to the rising edge. So now I need to remember. Oh, right. Okay, I need to enable the register first. Then when I clock, it updates to one. Falling edge doesn't do a single thing. Rising edge, it updates again. Falling edge, it doesn't do a single thing. Rising edge, it updates again. So this is a counter, okay? Every time we have a rising edge, the counter increments by one, which doesn't seem like a very useful thing. But inside the processor, there are two main counters, okay? One is called the program counter, and then the second one is called the microcode pointer. Every time you have a sequence of things to happen, and you say, okay, these things need to happen in this particular order, and they cannot all be happening at the same time. They need to be coordinated. Then you need something like this to keep track of, oh, which step am I on right now? You need a counter. Are there any questions about this particular circuit? This is the one of the simplest and yet most useful clocked circuit. In other words, everything, the timing of the update is controlled by the clock. Yep. All right. Well, okay. To answer that question, we'll answer in two ways. The first way is to ask you what happens in this math, because I want to help you guys study. Not really, but just so happens that this may help some of you study. Hmm? Nope. I'm just going to use 1 1 1 1 1 1 1 plus 0 0 0 0 0 0 0 0 1. And what do we get? Okay, so we're going to go for the whole thing. Okay, we're going to go for the Q. We're going to go for the K. Okay, and then we go for the sum. All right, because you should know this already. Okay, your exam one is on Thursday, and something like this, okay, is going to be in your exam, guaranteed. Even though I really have not really made the questions yet. All right, so Q is not even dependent of whether whether we're adding or subtracting for binary. Okay, for other bases, yes, it does. Okay, for bases other than two, whether the Q row how the Q root is computed from XY depends on, oh, are we adding or are we subtracting? But for binary, it's the same. It is basically just the exclusive OR between the X and the Y. So that means, oh, okay, I can figure this out pretty quickly. Okay, I can just overwrite. This is going to be a 0. This is going to be a 1. This is going to be 1, 1, 1, 1, 1, and 1. Okay, easy. So in this case, I'm going to assume K0 is a 0 because I don't have any prior addition to deal with. So that's a 0. So now I look at this one here and go like, okay, what should that be? It should be a 1 because x0 and y0 are both 1s, and the carry function is the conjunction between those two bits. So now this is a 1. What about this one here? It should also be a 1 because k of I plus 1 is c of xi, yi, or c of qi, ki. In this case, it is the qi, ki that contributes the 1. Okay, so as I said a little bit earlier, I might be accidentally helping you to study for the exam on Thursday. I don't mind that. It's just that it was not my actual intention. I want to make that clear before people start to think that, oh, tech is so nice. No, I'm not. And I like that reputation. It's kind of like if you catch Darth Vader petting a kitty, do you think you will live? The answer is no. The kitty lives, not you. The witness of Darth Vader being just, oh, look at that kitty, oh, this is so nice. You go like, oh, I witnessed this. You're dead, so dead. Hmm? Yes. The cat will start to have a little helmet and the uniform. All right, not physically. Just because you're walking doesn't mean you're alive. Oh yeah. Sounds like a good sci-fi to me. Yes. All right. Yes. I sense a disturbance in the force. Yes. All right. So what about S? Okay. S is the exclusive OR between the Q and the K. Okay, because it's the R function. So now it's, oh, okay, that's a 0, that's a 0, that's a 0, that's a 0, that's a 0. They're all zeros. Okay. So that's the first way I answer your question. I did mention there too. So the second way to answer the question is to go back to Logisim and turn this to FF. Okay, so you can do that. Okay, you can click using the poking tool. You can poke a register and then you can type in the hexadecimal digits into the register to force it to a particular content. So now when I have the next rising edge, it would do the same thing that I demonstrated a little bit earlier. So this is a falling edge, nothing happens. Now it's the rising edge, and you can see how it goes from um, FF to 00. Yes, it does not. Okay, so if you want that to be recorded or at least reflected so that you can see it, you need an output pin connected to C out. So in this case, C out corresponds to K8 in our nomenclature. Okay, because K8 is the hanging carry bit that does not match any of the other bits. Okay, that's the overall carry in this case. So let me repeat the experiment. Okay, so I will repeat the experiment here and turn this into FF. Okay, so we'll use the poking tool. And the moment I turn this into FF, you will see C out becoming a 1 because the calculation is instantaneous. It's just that I'm not updating the register yet. The output of the adder is already correct. It's already all zeros here with a overall carry or K8 being a 1. But the register is not updating because I do not have the rising edge yet. Yep. So if I turn it to FE, then we'll take one more step to do it. So when it's FE, this will be dark. And then when I update it, the moment I click this one more time, the register will update to FF, which means we have FF presented here, 0, 0 over here, and a 1 here, which basically means we end up with FF plus 1, and that will turn into a 1. So we'll take a look. That's exactly what happened. Yep. You can, so the way you do that is you can have the carry bit here. Let me see how we can do that. Well, this can serve as a clock to another circuit like this. So now you can count the number of times the carry has turned from 0 to 1. So you can kind of nest your designs like that if you want to. So I did lie a little bit, okay? I wasn't exactly accurate because in this particular example, y should be all zeros. It is k0 that is a 1. If I want to reflect the actual circuit, this is what's happening. But it still end up to be the same to end up to have the same result because in this case q would be a 1 and 1 plus 1 would still be a 0 contributing to this one over here. So it will still end up with exactly the same bits, but this is better matching the circuit that we saw earlier than the previous example. So are we good? Yep, go ahead. Um, More bits is just easier. Yep. hmm Yep. Yep. Exactly. And this is also so relating this back to remember, something is supposed to hit the watchdog every so often. So inside most computers, okay, I would say inside all computers these days, inside the processor is a device called a timer. A timer is kind of like what we saw earlier, except it counts down instead of counting up. So it always starts, you can control, where it starts the countdown, and then when it counts down to 0, then it will cause what we call an interrupt, where the processor, where the operating system, I take it back, where the operating system has a chance to go like, oh, I see that 15 milliseconds has passed. Let me see what I need to do. Oh, one thing, the first thing is to hit the watchdog so that the watchdog does not time out and start to reset the whole system. And then plus a whole bunch of things like keeping track of the real time and whatnot. So the timer is the opposite of what we just saw here. Imagine that instead of having an adder, you have a subtractor. But every time it runs out, it is reset to a specific value. So that's basically what a timer really is. It's a countdown timer. But when it resets, the value that you use to reset the counter is programmable. So now you can program the delay between the timer you're going off. Yep. It why wouldn't it reach 0? Okay, so you're talking about code outside of the interrupt surface routine. So to get to the timer, to even talk to the timer, you need to have certain privileges, and your user space, your programs do not have the privilege to touch any I/O devices. So that's the first hurdle that you have to go through. Okay, well, wait, don't go yet. You guys need to know the access code of today's lab. Let me move it into the right place because otherwise you cannot find it. Oh, I cannot find it anymore. Right here. All right. So this one is supposed to be right after this. There we go. All right. The access code is DFF all uppercase. Alrighty. I'll see you all later at the lab.